Hi guys, welcome back here at the EC Engineering Tutorials. So, continue na tayo sa discussion natin for water measurement. So, puntahan lang natin yung average area velocity method. Okay, so area velocity method. So, the rate of flow of water passing a point in an open channel is determined by multiplying the cross-sectional area of the flow section at right angles to the direction of flow by the average velocity of the water. So the cross-sectional area is determined by measuring the depth at various locations, and the depth can be measured by different methods like sounding rods or sounding weight or eco depth sounder for accurate measurement. Okay, so parang ganito, no? Yung nakikita natin. So meron tayo ditong mga segment W1, W2, W3, and then we have this boundary section, no? So bali ito yung stream section for average velocity method. Okay, so for the discharge calculation, the entire cross section is divided into several subsections, and the average velocity at each of these subsection is determined by current meter or float. No? So the accuracy of the discharge measurement increases with the increase in the number of segments. So some guidelines for choosing the number of section are as follows. No? A is the discharge in the segment should not be more than 10% of the total discharge. The difference in velocities between two adjacent sections should not be more than 20%. And the segment width should not be 1 over 15 or 1 over 28 of the total width. Okay, so next slide is the calculation for the discharge. So the total discharge is calculated using the method of mid-section, and it has been considered that the section is divided into n-1 sections. So we have Q, which is summation of the individual discharge in the I section. So starting from 1 to n-1. So ganun, no? So for the first and the last sections, the area is calculated as follows dito. So we have y1 minus yung average nung w1, where yung average in w1 is just w1 plus w2 divided by 2 squared over 2 w1. So now the q1 is equivalent nung area 1 times velocity 1 average. Okay, so we have also float method. It is inexpensive and simple method. No? So this method measures the surface velocity. So mean velocity is obtained using a correction factor. So the basic idea is to measure the time that it takes for the object to float at a specific distance downstream. So bali yung velocity at the surface is equivalent nung travel distance natin over the travel time. So because the surface velocity are typically higher than the mean or the average velocity, so we have this correction factor K. So generally, it ranges from 0.8 for rough beds to 0.9 for smooth beds. So commonly used is the 0.85 as the value of K. So step 1, we choose a suitable straight reach with the minimum turbulence, ideally at least 3 channel width long. Step 2 is to mark the start and end point of your reach. So you have A and B. So if possible, the travel time should exceed 20 seconds. So step 4 is to drop your object into the stream upstream of your upstream marker. And step 5 is to start the watch when the object crosses the upstream mark and stop the watch when it crosses the downstream mark. No? So bali, kinukuha natin yung travel time ng float object natin dito. Step 6 is you should repeat the measurement at least 3 times and use the average velocity in the further calculations. Okay, so
flow can be calculated using the float method with a measuring tape, small plastic bottle, and a timer. Flow is best measured in a run where water is flowing, and when there are two observers. First, determine the float distance by measuring and marking 2 points along the length of the channel. Try and get at least 10 feet. This length will be your distance. Next, measure 3 depths across at the channel cross-section. Average those 3 depths, and this is your depth. Next, measure a representative width of the stream, and that will be your width. Now let's float the bottle. Partially fill the float bottle with water. One observer stands at the top of the reach, and the second observer stands at the bottom. The observer at the top tosses the float bottle into the channel and calls out "start" when it crosses the upstream point. The other observer will start the timer. And as soon as it crosses the second point, they'll stop the timer. Repeat this toss process 3 times and average the 3 times together. Use this average as your time entry. Now you can determine the flow in cubic feet per second by multiplying the width and average depth by the product of the distance and the time. A correction factor is commonly used because surface flow is faster than flow in the water column. Time. Flow can be calculated.
So yan, no? So ganun yung float method. So
hi, I'm Zach Samsel and this is Gabe Acosta, and today we're going to measure stream flow by floating an orange here along Ackerman Creek. Hi, I'm Zach Samsel from Thenoliville Pomo Nation Environmental Department, and today we're going to measure stream flow, aka discharge, which is the amount of water that's flowing between a cross-section at any given point. Stream flow can vary depending upon the amount of rain, snowpack, and whether or not it's the warm or wet season. Having said that, we're going to measure the stream flow with some tools that you might have at home and the help of our special assistant.
Hey guys, Gabe Acosta. So today we're measuring the flow of a stream. Flow is important because it defines the shape, size, and direction that the stream is going to take. This is important in water quality and habitat location.
And let's not forget that stream flow and velocity help us to understand what type of organisms live within the watershed, which helps us understand their different migration patterns and spawning areas. With that in mind, let's get started. Here's a list of the things that you'll need: string, a waterproof yardstick, an orange. You'll also need camping stakes, scissors, a fishing net to get the orange out of the stream, measuring tape, and twist ties. Let's get started, shall we? The first thing that you want to do is mark an area along the creek. We used camping stakes and a string to mark the beginning line, and then 20 feet away from there, we measured another string, and this is basically going to be our racetrack, if you will, where the orange is going to float and we're going to time it. After you've strung the strings, we measured it and then divided that by 4 and marked it into 4 even intervals that are marked right here. That's going to help us to get the average depth of the creek by using a yardstick. Once you have both of the lines marked, we're going to go back through, we're going to check the depth at each of these, and we're going to write it down on the handy EPA stream flow calculation sheet. Now we're going to go to each one of these 1/4 intervals and check the depth of the creek so that we can take a composite average that's later on used in the calculation. And then obviously each of the stakes at the ends are zeros. We'll get deeper into the calculation once we've actually timed the orange. Now comes the fun part where we're going to float this orange and measure the amount of time it takes to travel from this string to the next one. Are you ready? Don't go too fast, buddy. Boom. And that's all it takes, folks. Now it's time to do some math. Let's take this show inside. Now that you've filled out the EPA data form, we're ready to figure out the average cross-sectional area by using the data from the data form. We're going to start out by calculating the total width and then calculating the total depth. In calculating the average depth, we're going to take the total depth and divide that by the 4 intervals we marked on the line. And that gives us a total of 0.81 feet for the average depth. Then we take the total width, multiply that by the average depth, and we get our number for section 1. And now we're about to do the same for section 2. We're going to total up the total width, and then we're going to total up the total depth. Just like last time, we're going to take our total depth and divide that by the 4 intervals, and that'll give us the average depth. Then we take the total width, multiply that by the average depth, and we're almost ready to calculate A. Now we take the figures that we got for section 1 and section 2, divide those by 2, and that gives us A, an answer of 18.9 feet squared. Now we're going to calculate L, which is the length of the stream reach. The next part of the equation is determining the coefficient. It'll be 0.08 if your stream has a rocky bottom, and it'll be 0.09 if the stream has a muddy bottom, as per the EPA guidance. Now we're going to determine the average travel time by totaling up all 3 of the timed runs that you did along the stream to determine the average time for all 3. Total them all up, divide it by 3, and you've got your average time, and that figure will be T. So to do a quick recap, A is 18.9, L is 20, C is 0.08, and T is 43. And now we're going to calculate flow, which is the average cross-sectional area times the length times the coefficient divided by the time. And that ends up giving us an average stream flow of 0.7 feet cubed per second.
Okay, so we have here a current meter showing rod suspension with double N hanger and round weighting base. No? So ito yun, no? Yung current meter. So in the area velocity method, current meters are generally used to measure the velocity of flow at different sections. So the current meter consists of a small revolving well or vane that is turned by the movement of water. So it may be suspended by a cable for measurements in deep streams or attached to a rod in a shallow stream. No? The propeller is rotated by the flowing water, and speed of the propeller is proportional to the average velocity of the flow. So corresponding to the number of revolution, the velocity can be obtained from the calibration graphs or table. So we have 3 general types used. We have the propeller and cap type. We have also the propeller type with vertical axis and the electromagnetic probe. So here, so ito yung propeller type na current meter. And ito naman yung electromagnetic probe showing the teardrop shape sensing unit meter and a rod used in measuring the velocity of the flowing water. So ito naman yung mga procedure for velocity measurement using the current meter. So stretch a tape across the channel cross-section, divide the distance across the channel to at least 25 divisions, and use closer intervals for deeper parts of the channel. So yan, no? Second is to start at the water edge and call out the distance first, then the depth, and then the velocity. And then we stand downstream from the current meter in a position such that the velocity is less affected by the emitter, and hold the rod in a vertical position with the meter directly into the water. So to take a reading, the meter must be completely underwater, facing the current and free interference. So the meter may be adjusted slightly up or downstream to avoid boulders, knocks, and other obstructions. So the note taker will call out the calculated interval which the meter operator may decide to change, taking readings at close interval in the depth, high velocity parts of the channel. And we record the actual distance called out by the meter operator as the center line of the subsection. So we just take 1 or 2 velocity measurement at subsection. So if the depth is less than 60 centimeter, the measure velocity once for each subsection at 0.6 times the total depth. So doon natin nilulubog yung current meter, no, at 0.6 nung total depth. So if the depth is greater than 60 centimeters, so measure velocity twice at 0.2 and 0.8 times the total depth. So dalawa kung greater than 60 cm, so dalawang beses natin sinusukat yung velocity at 0.2 of the depth and 0.8 of the depth. So the average of these two readings is the velocity for that subsection. So we allow also a minimum of 40 seconds for each reading. So the operator calls out the distance, then the depth, and then the velocity, and the note taker repeats it back as it is recorded as check. And then we calculate the discharge in the field. If any section has more than 5% of the total flow, subdivide the section and make more measurements. So current meters are designed in a manner such that the rotation speed of the blades varies linearly with the stream velocity, and this can be expressed by the following equation, that velocity is just equal to A multiplied by ns plus B. Yung V dyan, yan yung stream velocity at the measuring site in meter per second. Yung A and B dyan, yan yung mga constant ng meters, no? At saka yung ns, yan yung revolution per second ng meter. So to determine the constants, yung A and B, which are different for each instrument, the current meter has to be calibrated before use, no? So this is done by towing the instrument in a tank at a known velocity and recording the number of revolution, ns. So this procedure is repeated for a range of velocity. So that is for calibration, no, nung current meter natin.
That we'll be conducting is the flow measurement using current meter and surface floaters. The objective of this experiment is to determine the stream flow velocity using current meter and surface floaters, to measure the wetted area, cross-sectional area of the drain, and to compute the stream flow rate.
The following are the steps to assemble a current meter. Connect the three rods with each other to make up the shaft of the current meter. After the shaft has been connected, attach the propeller towards the base of the shaft and tighten it. Add the base plate at the bottom of the shaft and move on ahead to tighten any joints or attachments of the current meter. Now screw on the wire on the propeller and the other end of the wire at the top of the shaft. Similarly, connect the other end of the wire to the sensor in the color coded sockets. These are the steps to assemble a current meter.
So in order to start the experiment, first we will measure the width of the cross-sectional drain. Then the measured width will be divided into 3 sections. After that, the width of the drain will be measured by the current meter, and the propeller will be placed at 0.6 into the depth of the drain section. So let's move on to doing our experiment. The first step will be to measure the width of the drain. As we can notice here, the width of the drain is 94 centimeters. So we have divided the width of the drain into 3 sections. The first we will take in 25 centimeters, and we will measure the depth of the water at this section. For the first reading, we have already measured the depth of the this drain, it came out to be 16 centimeters. So we have placed the propeller at 0.6 of the depth, that was 9.6 centimeters. So now let's move on to take the reading from the hydrometer. The hydrometer calculates the number of revolutions done by the propeller. And it automatically stops after 30 seconds. So 183 rotations were done by the propeller. The second reading we will be taking at 50 centimeters, where the depth was 20 centimeters to 25. One 163 rotations in 30 seconds. We measure the depth again in 30 seconds, which the surface floater takes.
Okay, so yun yung process for current meter. So let's have an example here. A current meter used in determining the velocity of the stream of a river has a constant values A, which is 0.345, and B, which is 0.033. So the survey lasts 60 seconds with a recorded number of revolution of 20. So find the velocity of the stream at the point of consideration. So we just use this formula. So given yung A, which is 0.345, given yung number of revolution for 60 seconds, we have 20 over 60. And then we have the value of B, which is 0.033. So therefore the velocity of the stream at that point in consideration is 0.148 meter per second. So we have also other example here. So find from the current meter notes taken on San Agustin River, so the values are tabulated as follow. So we have this distance 23, 35, 50, 85, and 100. And we have also this different depth of water. And the depth of observation is also shown here, and the time in seconds, the number of revolution, and also the velocity at that point, no? So, yung tanong is ano daw yung total discharge in liter per second, ano daw yung total cross-sectional area in square meter, and ano daw yung mean velocity in meter per second. So, to solve that, first we need to compute for the mean velocity. So, since given yung mga velocity for specific point, so we can compute for their mean velocity. So, we have BA, which is 0.21. At point B, we have 0.275, and at point C, we have 0.18. So, velocity 1, we have 0.105. Velocity 2, we have 0.2425. Velocity 3, we have 0.227. So, ito yan, no? Itong main velocity, ito yung ginamit natin to calculate also for the V1, 2, 3, and 4. Okay? So, we have now also the areas. So, area 1, area 2, area 3, and area 4. So, we can now get the value of total area, which is 157.75 square meter. And using the values, using continuity equation, which is Q equals area times velocity. So, we have area and we have also velocity. Then, we can have this discharge Q1, 2, 3, and 4. So, thus the total discharge is 32.175 cubic meter per second. So the key equation is we have this Q equals area times velocity. So we have the Q total and we have the area. Thus our velocity is 0.204 meter per second. So we have also another problem here, sample problem. So data pertaining to is stream gauging operation at a gauging site are given below. So the rating equation of the current meter used is 0.63 ns plus 0.08 meter per second, where yung ns the revolution per second. So we calculate the discharge of the stream. So again, given yung distance from the left na water edge in meters, the depth and the revolution of a current meter keep at 0.6 of the depth, and also the duration of the observation. So yung nakita natin na video, ito yung makukuha natin. No? So we have this distance, we have this depth, we have this revolution, and we have this duration. No? Okay, so yan. So ito yung magiging calculation natin. So which is tabulated here. No? So we have this distance, we have this area of width, yung depth, yung number of revolution per second, and then we can now compute for the velocity using yung 0.63 ns plus 0.08, and we can have also this segmental discharge, which is area times velocity. No? So to sum up, the discharge in the stream is 23.4 cubic meter per second. Okay, so another method used in water measurement is itong tracer method. So in the tracer dilution method, the tracer solution is injected into the stream at one point, and the tracer is measured at a point downstream to the first point. So knowing the rate and concentration of the tracer in the injected solution and the concentration in the downstream section, so the stream discharge can be computed. So either constant rate injection method or sudden injection method may be used for determining the discharge of the stream by the tracer dilution. So the constant rate injection method, so in this method, the tracer solution is injected at a constant rate into the stream till a constant concentration of the tracer in the stream flow at the downstream sampling cross-section is achieved. So I'm not really familiar with the tracer method. No? Anyway, ito naman yung equation niya. No? So you have this discharge of the stream multiplied by the background concentration of the stream plus the rate of flow of the injected tracer solution multiplied by the concentration of the tracer solution injected on the stream, which is equal to the discharge of the stream plus the rate of flow of the injected tracer solution, and then multiplied by the measured concentration of the plateau of the concentration time curve, which is given here. No? So we have this C2, which is dito sa plateau natin. Okay? So yung Q is just equal to, simplifying this equation, we have the discharge, which is C1 minus C2 over C2 minus CB multiplied by Q. So ganun lang. So ito yung tinatawag na concentration time curve dito sa tracer method. So we have this salt dilution gauging or the tracer method. So ito yung process niya.
Discharge is an important variable that governs many aspects of stream function, such as habitat diversity and rates of nutrient export. It is also a direct measure of the amount of water available to meet in-stream and extractive water uses. The most common approach to measuring discharge is the velocity area method technique, which involves measuring the water depth and velocity at points across the stream using a flow meter. It is, however, sometimes difficult to use the velocity area method in small streams. An alternative method of stream gauging involves injecting salt and determining its dilution following complete mixing into the flow. Salt dilution gauging means that the discharge can be measured without wading across the stream, which can be hazardous in many fast-flowing turbulent rivers. Common table salt, sodium chloride, is popular for dilution gauging for three reasons. First, table salt is cheap and readily available. Secondly, it can be accurately measured in the field using an electrical conductivity meter. And thirdly, it is non-toxic or damaging to the environment. You will need four main pieces of equipment to carry out salt dilution gauging. Firstly, you will need sodium chloride in the form of table salt. You will need a bucket and something to stir the water in the bucket. And finally, you will require an electrical conductivity meter, which can be borrowed from your department. The first thing you need to do is to measure the electrical conductivity downstream. You will need to collect a bucket of water, like you can see Lucia doing here. You then need to dissolve a known quantity of salt into the bucket of river water that has been collected. Here you can see Rachel adding 1 kilogram of salt into the bucket of water. In order to ensure that the salt is dissolved fully, you should stir the mixture thoroughly, as you can see Summon doing here. You then need to throw the bucket of river water with the known quantity of dissolved salt into the channel. It is recommended that you inject the solution upstream at a length of approximately 20 times the width of the river. From when the salt is thrown in, take records of the conductivity meter every 5 seconds until the conductivity stabilizes, and record these results.
So that is tracer method. So we have this example. So a 12 grams per liter solution of a tracer was discharged into a stream at a constant rate of 15 cubic centimeter per second. So the background concentration of the dye in the stream water was found to be 2 parts per billion. At a downstream location sufficiently far away, the dye was found to reach an equilibrium concentration of 7 parts per billion. So estimate the stream discharge. So we have this equation, given yung Q, given yung C1, tsaka yung C2, tsaka yung CB, no? Like plug and play, we have now the stream discharge of 60 cubic meter per second. Okay, so I think that's it, no, for area velocity method and tracer solution method.